Okay, too much to cover again today. Sorry, you guys. Representation geometry. So, okay, so I'll just dive in. So we've had a few readings, and calling you guys. Actually, how you here? Yep. Had an initial question, and so now on right now. Hi, you. What was your question?
So what does it mean for the model linearly represent?
What does it mean for the model to linearly represent truth, right? So one of the papers you guys read, first one was this geometry of truth paper, and they had these nice scatter plots in them, which was supposed to be suggestive of something. So none of the paper is actually, it's actually really hard to find any modern paper pin down a definition of what it means for something to be linearly represented. But this is, so I'll make up a definition. And you can see this in some old papers. This is an old definition, right? So let's say you have a whole bunch of neurons in your neural network, and you have the numbers that say how much the neurons are activated in a vector X, right? And for a different stimulus, this X will be different. That's X is your representation. What it means for something to be linearly represented in that vector is just this, is that you've got some scalar, you've got some attribute, some property A that you care about. Like, is this sentence true, right? Or is this AI being truthful or not? Something like that. That might be your scalar output. Maybe a big number means yes, true. Maybe a small number means no, false, right? And what it means for it to be linearly represented is that you can just do what's called a linear readout of the neurons. You can just take a weighted sum of all the neurons, or equivalently a dot product by some fixed vector W. And that will give you some number, which is just your readout of this property. Now, for truth, maybe the property is true or false. So, I think there's some details here that I've omitted. Like you might threshold it at some value. Say if it's bigger than the value, then you say it's true, and it's smaller than the value, you say it's false. And it might not be 100% accurate, but it might be good enough. It was 80 or 90% accurate. People would say, "Oh yeah, this information is in here. It's linearly readable." Does that make sense? That sort of answer the question. So that's all it means for something to be linearly encodable. Okay, so so it's all about around dot products. Like everybody learned what dot products are from linear algebra. And then when you see a scatter plot, like what Sam Marks put in this paper, you can see that this is the reason he thought it's obvious after I put my scatter plot that this is linearly readable, because you can see this clear separation. So he didn't put this vector here, but this vector would be like the weight vector W that you're dot producting with. And so if you dot product with this thing, then whenever the dot product is positive, it's in the red area. If it's negative, it's in the blue area. And when you do the linear readout, you can make a little histogram of like how many dots, were negative and how many dots were positive. You did this. So, I recommend if you, do this with your own data, make histograms like this, so you can kind of see that how well it's separating, different things. So all the things that are supposed to be negative over here, all the things that are supposed to be positive over here. So why do people believe that anything would be linearly readable in a neural network? The reason is because it's how neural networks work internally. So, we draw all these network diagrams of a neural network where every neuron takes as input a weighted sum of the outputs of other neurons. All this is a dot product. All this is linear readout. So if you think of a deep neural network, all it's doing is at every layer, every neuron is one of these operations. It's one of these linear readouts. So the hypothesis is that all the useful information in a neural network maybe is actually able to be read out linearly, because if it wasn't able to be read out linearly, the neural network itself wouldn't be able to access it, right? Because that's all the neural network has as a tool for reading its own information. So that's sort of the hypothesis. Yes, go ahead.
But does this linearity take place even after we deliberately add non-linearity to the
Yeah.
network.
So then after, so you're saying, oh, typically you add a little nonlinearity
Yeah.
after you do this
Just
to threshold it. That's right. And it's the same detail here where I'd say, oh, you might add a thresholding or something like that. And so that's equivalent to, let me, I'll come to that in a minute. But that's sort of equivalent to saying, hey, at some point we might want to draw a separating plane here. So all linearity really means is even if you have like a separating plane where you're going to have something nonlinear, like a decision, with the linear readout, all you can really do is slide that plane around. You can't make it into a curve or something like that, but you just got to slide it around. Now, obviously, you can make curves and stuff if you have multiple layers of a neural network. But if you just have one layer, then all you can do is basically read out a straight line. Read out something linear. And so the linear readout hypothesis is that, well, the neural network is going to curve all the data around, but at the moment that it's got to use it in a useful way, then maybe it's the useful information is linearly readable at that moment, and you should be able to read it too by finding the right linear model. Just put on. So that's what all these papers that I assign are all about, this linear readout thing. Okay. Okay. So I like this other question. Eunice asked this question, and Kabbalah asked another related question. Yeah. So what was Eunice's question?
I think he's online.
Eunice. Yeah. Is your audio working? Do you want to ask your question?
Yeah, I am on Zoom. So, can you hear me?
Yes, it's beautiful.
Cool. So all of the papers were kind of try to prove that concepts are linearly represented, but are there any cases concepts are kind of nonlinear or clustered, or I don't know what are the other options?
Yeah, what are the other options? If everything's so linear, then like what's not linear, right? I mean, I think that's a really good way of understanding like what it even means to have a hypothesis. If it's not falsifiable, then we're not even doing science, right? So yes, you can definitely have nonlinear encodings. My clearest example is actually from the oldest neural network paper in history. So who's ever heard of the Rumelhart, Hinton, and Williams paper? Anybody ever heard of this paper? Yeah, okay. My own grad students have heard of it because I make them read it, right? So this is the first neural network paper ever. This is what won Jeff Hinton the Turing Award. And it's where they basically told everybody, oh, you can train neural networks using backpropagation. And so now a lot of people, including what's his name? The guy who thinks he invented everything. No, Yannicka did invent everything. Schmidhuber. Yeah, Schmidhuber. Who invented, LSTM and several things. So he is an inventor of a lot of things, but he likes to claim he invented them. So Schmidhuber always, this is his least favorite paper because he says, well, Hinton didn't invent backpropagation. Isaac Newton invented the idea. Why did Hinton win like the Turing Award for this? And then furthermore, not just Hinton, but like all these other graduate students between Isaac Newton and Hinton, went into it a lot more than Hinton did. So Hinton wrote this one pager for Nature and then won the Turing Award. Like, why did he get this credit? And if you go and read the paper, the main idea of the paper is not that you can use derivatives to optimize the system. Everybody knew that, right? The main idea was an interpretability thing. He's like, after you train a bunch of neural networks and you look inside them, they learn really interesting representations. And so he has a series of neural networks where he tears apart each one after he's trained it with gradient descent to show that. So he's like the first interpretability researcher. It's really what he won the award for. And so, but his neural networks are too small, and they didn't follow. Like a lot of them didn't follow the principles that we generally see in very large neural networks. So, for example, this is one of the networks we studied. It's a network with I think 8 neurons, 9 neurons, something like that. If you count the input nodes as neurons, which maybe you wouldn't even count because it's just inputs, in which case it just has 3 neurons, right? and it's supposed to detect like palindromes or pixel patterns that are the same on the top as at the bottom, and they're mirrors of each other, right? So he trains this thing as a mirror detector, and if you put a symmetric pattern in, then this output will say, yeah, I got a mirror. And if you put a not symmetric pattern in, it'll say it didn't. It took him, a long time, many hours to train this thing. You could probably train it in a millisecond today. And then these are the trained weights that come out. And the interesting thing, if you think about this encoding, it's very non-linear, right? What it learns. And why is it non-linear? It's because these neurons that he's learning have learned this encoding, which is very strange. For example, if this neuron reads 3.6 is what comes into it because of the weights 3.6, it means everything is 0 except for the first pixel, right? And if it reads like negative 7.1, it means everything's 0 except for the second pixel, right? And if it reads negative 3.5, it means both pixels 1 and 2 are on. Now, the reason this is non-linear is because linear things, they scale their meaning when you scale the value. And so really what should happen is if you like scale this up, or made this negative, it should be like the pixel 1 is like negative or something like this. But if you doubled it, it should be like pixel 2. It shouldn't have anything to do with pixel 2. It should have to do with pixel 1. But it changes its meaning. And then you can kind of see when it gets to 14.2, it means, it has nothing to do with pixel 1 and 2. It has to do with pixel 6, right? So what he's done is he's learned this neural network, which splits up the number line. And for every different part of the number line, it has like a pretty unrelated semantic meaning. He's using arithmetic coding here, or this neural network has learned how to do arithmetic coding, but that's different from a linear representation because it doesn't scale its meaning with the scale of the value. Like for truth, it would be like, if something was already true and you doubled it, it would just mean like more true. Like I'm more certain that it's true, right? And then there's some threshold when it's false. And then if you doubled it and made it more false or more negative, then it'd be like, that's more false. I'm more certain it's false or something like that, right? So, but here it doesn't work like that. And so, so there's definitely, and it is a neural network. So like neural networks can learn nonlinear encodings. It's just that we tend to not see them in large networks. It's like they're pretty hard to learn. They don't show up that often, but it's not impossible. Makes sense? So actually, I've always been puzzled by this when I was studying neural networks. Have you ever thought about this? Like how much information can be stored in one neuron? Like that's weird, right? Because a neuron is like a real number, right? How many digits go in a real number? 5, 6? How many digits can go in a real number? Like infinite, right? I don't know. I guess it depends on the hardware you choose. Yeah. But that's not real. That's a floating point number. What about a real number? Like what if it was like a biological neuron? It's like a real, like it really activates, right? What's a real voltage? Like how many digits can go in a real number, like a real biological neuron? It's like infinite, right? So that leads you to this puzzle. It's like how much information can you store in a real number? Like if I write out a real number, like I could encode like the whole Declaration of Independence as ASCII and then put them in the digit as a real number, and like a single neuron should be able to encode that, right? So that's what's going on with these neurons here. It's like like each one of these neurons is like encoding a whole six bit pattern, and neural networks are able to learn this if you train them hard enough. But it's it's really weird, right? Like you might extrapolate this and do sort of the Declaration of Independence. You're right, but it turns out that's really hard to train networks to do this. And what we tend to learn is networks that represent everything linearly. There's a way out of, so if people are machine learning people and are puzzled by this thing about like how can a single neuron encode an infinite number of bits, the thing to look at is all the variational people, like variational autoencoders and things like this. They work through the mystery of how to control the number of bits in a neuron, and it's about reasoning about the neurons are really operating in a noisy environment. You have to read them about the noise that they might have. Okay, so this is what nonlinear looks like, but a lot of stuff is linear, including I'm like like it frustrates me a little bit when people say, "Oh, this is nonlinear," and what they really mean is that some things are higher dimensional. They're not one-dimensional. So, like, I gave you a definition for linear readout, which is like for scalar things, right? But some things can be linear even if they're not scalar. So who asked this? So, oh yes, so Grace asked about this, and Arya asked about this. So, okay, Grace, what was your question?
Oh,
Maybe you didn't know you asked about this.
yes, sorry, I was, my question was about the sentiment paper.
Yes.
Saying, we found singular direction for sentiment.
For sentiment. And
then-
the neural
and then-
network is happy if this is a big number and sad if it's a
Yes.
low number, right? That's exactly.
And then in the limitation section, they say, but we don't really know if this means that we can't like decompose it into,
Might have more
it's
directions.
just a linear combination of a bunch of other directions. And so I'm like, what does it mean to say singular versus?
Right. Yeah. What does that even mean? Let me ask Arya to ask her version of the question.
I think I asked basically exactly the same thing.
Yeah.
Referring to the same limitation section.
Yeah. About this kind of thing. And so, so one way of thinking about what they're really saying is that, the neural network might have a more sophisticated representation of sentiment that we haven't bothered to decode. It might have, 10 attributes in there saying, I'm happy because, I'm feeling fulfilled, and I think that things are true, and I think that things are ethically good, and I'm feeling very full of and happy of food and good social mood. They might have a bunch of different axes of positive sentiment, and maybe what they're doing is they're finding that so if you had a bunch of different axes in a vector space, you could just define some weighted sum of all those positive types of sentiment and say, this is your average sentiment over all these attributes, and you could have one singular vector, which is just the average of all those vectors. And I think that what they're saying is, we think that there might be a chance that we've just measured some average vector here, and if you were to look closer, you might be able to find that you could decompose it into other vectors which add up to that average. And so now, what does this mean? What this means is that if you really wanted to understand sentiment, it's not a scaling, right? It might mean that there's 3 or 4 dimensions of sentiment that paper didn't get into. And is that linear? Does that make it nonlinear now? Because it's like 3 or 4 dimensions instead of 1. And so, and I think no, that's like an abuse of terminology. It is still linear, if you can do this. So if you have like an n-dimensional, attribute, like 3 dimensions of sentiment or something like that, if you can read them each out using a dot product, which is the same thing as having a matrix of weight vectors that you multiply by, right? Then it's still linearly decodable, right? And I think this situation happens a lot in large neural networks. In fact, we've seen it before. Like LogicLens does this. When we played with LogicLens for a day or 2, right? So when you look at LogicLens and you see, like it's decoding this vector to love, right? What you're doing is you're interpreting this using a 50,000 dimensional linear readout. Right? What you're doing is love and every other word in the vocabulary corresponds to a linear readout. And what you're doing is you're reading out like kind of the log probability that the model thinks that it should assign to love. But you're also reading out the log probability of every other word. And in LogicLens, we just happen to like read them all out, and then we just show you the top one. It's all that LogicLens is. That makes sense? But the process that we're using is a linear readout. So that what you're doing is you're taking this representation and you're shoving it through. Remember this little icon from the first class, right? You're shoving it through the decoder head, which is just, it's a fixed matrix that is inside the network. And then it comes out with this vector, which is like, amor is probability 3, love is probability 2, M is probably 1, or whatever, right? It just gives us these numbers. And logical link just shows you a visualization of that. That makes sense? Any questions about that? So another place that we saw a multidimensional readout was in the third paper. Didn't they understand the third paper? Was that confusing? Talk about the third paper. I like it a lot. But what they did, what Sheridan did in the third paper is set the weight matrix to some crazy matrix L sub C. Talk about where that comes from, which is the sum of some things. And then that was like a linear readout of some concepts. And so when Sheridan decoded, she traveled to Greece and looked at the representation of Greece. Sheridan is like reading out the representation of Greece into some multidimensional vector through this thing that Sheridan's going to look at, with some analysis. So it's another linear readout. Okay, sense? Yes.
So in the previous one, where we
Yes.
had only a scale and we could have used the threshold to figure out whether a particular concept is present or not.
That's right.
But here, if it is multi-dimensional, what are we doing? Are we doing norm of that, or are we looking in individual direction?
Yeah, so I think typically you bring it into a space that's meaningful to you, and then that space that's meaningful to you, I guess it's supposed to be meaningful. It's supposed to be like, oh, now it's up to you to understand what it means to be in that meaningful space. So somebody asked a question. I thought it was nice. I'll just ask a question because I don't see who asked it. About what if you had like spatial information that was decoded? Well, maybe when you decode the thing, the space is kind of like latitude and longitude or something like that, but maybe not exactly. Maybe you have to warp it a little bit for it to correspond to what we write down as latitude and longitude. But it has some comprehensive meaning. That's his idea. And so here in these vocabulary cases, then what we commonly see is you decode it out to a space whose dimension equals the size of the vocabulary, right? So 50,000, just like one number for every word. And then what comes out is a set of scores, a score for every word. And then the way that we interpret it is we tell us, well, we're interested in what the top scoring word is, what the top 5 scoring words are. Sense? But so it could be different, but I think it's accurate to characterize all these as exercises in reading some information clearly out of. Yeah.
I have a question. I think
Yes.
you briefly mentioned autoencoders.
Oh yes.
I was wondering if what you are explaining here is similar to the concept where with autoencoders, you can basically linearly capture one specific concept. And the more you go into one direction, the more
Yes.
that concept is present.
Yes, I think so.
Correct?
I think that's right. So basically, when I draw this kind of figure, it's intentionally evocative of, you can read this as a linear readout of the neurons, but also, neural networks themselves do this. So like an autoencoder is just an example of, network architecture that also is built on linear readout. And so when you do an autoencoder, it's trying to come up with a small number of scalars that are each some really informative, useful linear readout of the figure vector. Right? Sense. Okay. Let's see. Any other questions that I missed? Arya got her question. Guangyan had a question. Oh, I like Guangyan's question. Is Guangyan here?
Here.
Yes.
So yeah, on that paper, it's used like main data for k-means or logistic regression probe. And why should this method like recover sin access?
Right. The second paper.
And
Yes.
so
It was a little sloppy, but it's okay.
yeah, and what assumptions make like this sentiment clusterable in residue space?
Right. Yeah. Right. Okay. I'm not sure I'll totally answer the second one. I think the second one is a little bit empirical. What makes the network behave a certain way? Why is sentiment clusterable in a representation? I think this is part of the mystery of deep networks, right? We train them on a lot of data. We hope that they learn something useful. Usually when something useful is learned, they'll take the things that have a similar meaning from our point of view and put them close. things with a different meaning from afar. You know, why did they pick up on sentiment rather than some other thing that maybe they didn't pick up? We don't know, right? It's just it was useful for some reason, very draining. But you did ask this other, like the question. That paper, they applied the mass mean thing, k-means, logistic regression, PCA, DAS, right? And then they said, oh, we tried all these things, and they all came out the same. So, and that's not actually the lesson that I want you to learn from reading that paper, because they often come out different from each other. They are different techniques. It does, if the data is very well behaved, then they will kind of come out the same. I want to give you a little intuition for what causes them to be different in the main case that you'll see, right? And so okay, so here's like my favorite scenario. Okay, so suppose you had like a whole bunch of students in class, except different from this class because you've got like a final exam. Sorry, you guys don't have a final exam, right? And as a really hard final, half the students are going to pass the final, but half the students are going to fail the final. Oh, it's terrible! All these red students are going to need trouble. Fail the final, right? But we run the statistics and we find out that there's this interesting correlation between like how the students previously did in the class, right? And so what I'm going to do is I'm going to plot the two most important variables, which is their homework grades, right? And so here's like how the students did on the homework before, and who passed and failed. And then here's like the minutes spent on homework, right? So it's like the effort that they spent in the homework. And that's also like related to pass and fail, right? And so we plot all this stuff and then we say, oh, great, you know what I'm going to do? I'm going to figure out what advice to give to students next year. And the teacher, who obviously shouldn't be failing half the students, maybe they can do a better job at running their class, right? And so I'm going to run logistic regression and figure out what advice I should give. And so here's the logistic regression for a very realistic data set. So what logistic regression is doing is it's trying to find a separating plane between these two sets and with maximum margin and stuff like that, right? So I actually ran logistic regression on this data. It's not real student data, so there's no privacy issue here. I ran real logistic regression, and here's the advice. The logistic regression probe says, if you want to cross this line, you're on the bad side of the line. You're failing the student here, right? We want to get the students to succeed. We should do more of this. Go this way. What is this way? We should cross the line. What is this way? Means we should give everybody higher homework scores, right? So, teacher, you're scoring your homework too hard. Give everybody A's on the homework, right? And we should make sure that students spend less time doing it. Right? It seems like the total wrong advice, right? Doesn't it? Right. So this, like for me, this is a good example of why logistic regression can be an excellent way of classifying data, but it ends up with this vector, the probe vector, which is not a very good causal piece of advice on what to do to have a causal effect. That makes sense, right? And so when you hear people say, "Oh, correlation is not causality," and this and that, right? It's sort of related to this, right? It's a slightly different phenomenon, but it's related to this, right? And so that's one of the methods is logistic regression. You see this a lot everywhere. It's very easy to train a logistic regression probe. Everybody's taught in machine learning you should do this. So you see this all over the literature. But what Sam Marks advocates in his paper is, actually, maybe we want to use this other thing, much simpler than the training logistic regression. He gives it a fancy name, the mass mean probe. What the heck is a mass mean probe? You just take the average of all the green guys. That's the mean right here. Take the average of all the red guys. That's the mean right there. Right, and then the interesting vector is the vector that connects those two means. That's all it is. Make sense? And you can see how this would be more guaranteed to be causal than the other one, because it's so simple. It's like, what's your advice for all the red people? Well, the advice is you should be more like the green people. It's simple. And so, how do the red people differ from green people? Well, they get higher homework grades. That's good. Should work on that, right? But they also like study for more hours, right? So you should do that also, right? So there's no, like it's a simpler thing, and it's more guaranteed to be connected to causal variables. Yes.
Maybe this is a
Yes.
more of a data question than it's a modeling question,
Yes.
but it feels to me like the mass mean approach kind of implicitly assumes that you have like the same distribution.
Yes.
Whereas I could imagine like maybe you have two types of students that will fail final.
Yes.
Low effort, low grade, and
Yeah.
high effort, still low grade.
That's right.
And then if you have those two clusters, taking the average of that might not lead to
It also might not help.
or it might
That's
not
right.
the same way.
That's right.
So I'm just curious, would you categorize that as like a issue with the approach, with the data,
I
like
think
not
it's-
very counterfactual?
The way I put it, the way I think of it is like this: is you have this hope that somewhere in this huge signal that you've got, there's a causal variable. There might not be a causal variable, but you hope that somewhere in there there's one. And the danger of using the wrong kind of probe is that you might throw out that causal variable by accident. Like linear regression will do that a lot, right? But if you use the mass mean thing, if there's a causal variable in there, then you'll bring it along. You're bringing along all the variables because you're just like bringing along the means. You're not throwing anything out, right? Now, it's possible that your system's set up so that there's no causal variable in there. Maybe there's not. Like, there's no causality in any of the things you measured, right? And then this is not going to help that, right? You can't like invent causality where there isn't.
Maybe it's
right?
just like that linear combination of like different factors. You're trying to measure a combination.
Yeah, no, right, exactly.
Okay.
So there might be something causal somewhere in the system, but by the time you measure it, it's all downstream of causality, and none of your variables, none of the things you have are causal anymore. Right? It could be, right? So you often have this situation where you're downstream of causal variables, and nothing that you affect actually has a causal effect anymore. Right? Does that kind of make sense? You can have these systems as like, downstream of causal variables. It's like, oh, umbrellas. When people have umbrellas, it rains, right? Oh, that's very downstream of it raining. Like, if I give everybody an umbrella, it's not going to make it rain, right? How about rain boots and raincoats and all the other stuff, right? And none of it helps, right? It's not going to rain. We're still in a drought. Right? That's not the way to solve it. It's because it's all downstream. And so you might be in a situation where everything that you measure is downstream and it doesn't help, right? So, but if you do have something causal in there, then at least it won't throw it out. And then, so there's a second set of experiments we need to run inside a neural network to test for causality, and these sort of statistical techniques won't do them on their own. We just had to change things. Makes sense. But if you set all that fancy stuff up and you say, oh, the intervention I'm going to do is this LR probe direction, then it might still not work because you actually throw out the variable. Make sense? Or maybe even get it. So the other thing that Sam does is, Sam has this funny thing where, what does he say? Sam Mark says, when you use this mass mean thing, people want to use it as a probe. They want to like dot product by it and see like if something is truthful or not. He says, well, like if you just use a dot product, it's not a very good probe. You see that like the separating plane would cut through a lot of cases. It'd be easy to not get wrong here. And so what Sam points out is that the main cause for all these cases is that you have some covariance, you have some skew in your data. And the right way the way he likes to think about it is that it is a good probe, but first you sort of have to unskew the data. So he says, measure the covariance of your data, weighten by the covariance, and then you can cross that line. And that will tilt. It'll tilt all the angles so that, it basically, what a right angle looks like, after it's untilted will basically look like this blue line. It'll be a slightly different blue line. It's a different method. It's a method called linear discriminative analysis. But yeah, so that's it. So that's what Sam proposes in his paper, and Okay, so that's any other, is that sort of more than you wanted to know about how to find a linear direction? Okay. There's a lot of other things that people can do. So there are some other questions here. So for Courtney, oh, I missed you. Did I miss the T, Courtney? Courtney asked a question. Yuchi asked a question. Claire asked a question. Yeah, so some questions here related. Yes.
Yeah, so my question,
Remind me your name. I forget who's who.
Courtney here.
Courtney. Okay, great.
My question is about how the linear structure emerges like across the layers, and they said for some more complicated like tasks or structures, the later layers are better to find the linear
Right.
separation.
Yes.
How do you know when is the ideal layer to like cut off the
Right.
learning or pull out the linear structure?
Yes.
If there's so much variance, is there like a systematic way to do this?
Yeah, there's a couple systematic ways, and I'll show you. I'll give a little sense for that. And then let the other folks answer questions as well if I think they're related. So UT.
I think it's the same question, but I more focus on like which layer and which layer.
Okay, right. Yeah, because the transformer is this big grid with all the layers and all the tokens, and so right, a lot of possible things to probe. And Claire had a question. Yes.
I couldn't understand the summarization motif. I read that section like
Yeah,
three
what the heck
times.
is the summarization motif? Yeah, I apologize for this paper. I want to give you a little sense for what people are doing, but it's a little bit of a messy paper. I can explain it. Okay, so but it's related to the other two questions. So what's going on here is this. So you remember in Sam Mark's paper that he had this mysterious figure, this one, and then in paper number 2 they had this other heat map figure, this one. So both of these are different. They're different techniques, but from each other. But they're both what those researchers used to try to answer this question: which layer should we be probing, right? And which token should we be probing? And so, like, I really like Sam Marx's approach. What he did. So what he did is this is a causal analysis of tokens and layers. And so what Sam did is he took a single sentence. So he didn't even do this over the whole data set. He just took a single sentence. He said, Chicago is in Canada. It's not. Actually, I'm sorry, there's another sentence he puts after that. He says, this statement is, and you want to see if the model says true or false. Right? Chicago's in Canada. And the model should say false. Right? And then he runs it again. He says, Toronto is in Canada. The statement is, and he'd expect it to say true, right? So these two runs are really similar. And what he wants to do is he wants to look inside the model to see what variables are causal inside. So we're going to have a whole class around this type of causal scanning next week. But he does some causal analysis, and he finds that certain layers and certain tokens are more important than others. All these dark blue ones are the important ones, and he draws boxes around them and discusses them. And he says, well, this is sort of causally important, but not that interesting because it's like the city, Chicago or Toronto. But he says, oh, this is really interesting. At the period, at the end of the sentence, there's some really important representations that are causal, that cause the model to say flip true or false at the end. And so this was really fascinating because the period doesn't have any information in it, right? The period is the same between these two sentences, Chicago or Toronto. And yet the period has something in it that is decisive, in its representation has something decisive that somehow gets the model to say true or false and flip between them, between the sentences, even though there's nothing different about the period itself, right? And so what Sam hypothesizes is that something in the representation of the period, somewhere around layer, 15 or something, is like summarizing the truth of the sentence, right? So he uses this causal thing on one example to justify that, and it says so. Therefore, for the rest of the paper, I'm going to just look at the representations that are sitting here and see what the deal is, and I'll probe them and I'll scatter plot them and everything. So we'll look at this period, and so that's what he does. And actually, this is one of the pieces of lore that I'll just share with you. It's like these periods, these like punctuations at the end of sentences. The transformers, they put a lot of information on them. It's crazy, right? Like, this other paper is also doing something similar, other punctuation. So this paper is using a different approach. They're saying, okay, when you get to the end, John feels very, happy or sad or whatever, right? So like, okay, so you're about to make this prediction. What are the attention heads doing when they're trying to look back and try to remember what's going on to say, whether John feels happy or sad? So they find the relevant attention heads and they look at the heat maps and they say, oh, look, they're paying a lot of attention to the comma. This comma. What the heck? The comma seems so innocent, right? But actually, like there's something important there that the attention heads are looking at. So these are two different views of the same kind of phenomenon where, like, it looks like a lot of the punctuation is used by the transformer to deposit like summary information about what it understood about the phrase or what it understood about the sentence, and then later on, when it has to retrieve meaning, instead of going and looking at all the individual words, it often looks at punctuation for this information. So at least that's what we're finding, as it's a sort of a story that we've seen a lot. And so if you don't yet know how to do all this causal analysis, but you want to try to do some scatter plots and do some probes and look around, you could do worse than looking at a piece of punctuation, right? It might work. It might work. And if it doesn't, we can do the causal analysis for everything. But like, I recommend people just like look at the period at the end of the sentence. So like, if you're in the power team and you have sentences that describe somebody who's projecting a lot of power, and you have other sentences where sentences are somebody who's really powerless, and you want to see, does the model know the difference between these? Well, where would you probe? Maybe the period at the end of the sentence might be a good place to start. Right? Does that make sense? And same with all the other projects. Yes.
Slightly different, but when a model hallucinates,
Yes.
do you think there is like any pattern that, or has any work been done that tried to, because I think this is really new for me that the comma might hold power.
Yeah.
But like in the hallucinatory content, if there is like any pattern or any like certain, for example, I see a lot of digits keep on getting repeated when the model starts hallucinating.
Yeah.
So is there, has been like...
Yeah. So hallucination is a big deal. So a lot of people have done papers on hallucination. I don't think that I've seen any that relate it to the punctuation, but I'll share an interesting phenomenon. There's another thing that happens is, so there's two really interesting moments when a model is about to emit a token. One is right before it emits the token, and then you can see, like in the final bunch of layers, the model is like bringing together all sorts of information to make this really difficult decision of whether something is true or false, or whether some sentiment should be predicted a certain way, some arithmetic is figured out a certain way or something, right? So right before the token is predicted, you see all this interesting information converge on that right before token. But then there's this other thing that happens that after the token is emitted, and it's in the stream, and now the model's kind of going back auto-regressively and reading out what it just said. There's this other thing that happens, is it assesses what's going on. You have the token, and it'll assess whether it's true or false right after that. And so one of the hallucination results is that even when models make a mistake and they hallucinate something, after they emit the token, the wrong token, they put it in the stream, then immediately, one or two tokens after, the model will look at what it said, and it'll say, that doesn't seem right. Who said that? Right? Like they'll know that they made a mistake, which is really interesting. And so, and I think the hallucination paper. So I know that in my lab, the best place to find when a previous hallucination was a mistake is actually at punctuation. But there's been some other papers, so I don't know if other labs agree with that. Yeah. So okay. So let's see other things. Courtney also asked what layer, right? And there's simple things that you can also do. So there's these fancy causal things that you can do, but you can also just measure the margin, right? Just like a classic machine learning person would do, right? And so like a simple way of measuring the margin is like the Cohen's d statistic, which is, you know, you have your two classes, you know, your true things, your false things, your powerful things, your powerless things, whatever. And you have your direction, let's say your mass mean direction, and you just project everything on that direction. So then like how well are things separated? Well, you can just ask like how far are the means apart from each other? But now what's the scale that you should use for that? Well, you know, if the neural network happens to be outputting hundreds out of the neurons, then that would be a big scale. And if the neural network happens to be outputting, you know, 1/10 out of the neural network, that would be a small scale. But really what matters is like what's the relative scale relative to the general variance of the signals, right? And so what Cohen see is you take the difference of the means and then you just divide it by the standard deviation of what the data is looking like. And that tells you on a relative scale, like how much of the variation, you know, is you know, can be seen as a separation between these two classes, right? And so if you do this for real piece of data, then you'll often see, you know, graphs that go up and go down. Oh, this is two graphs. There's another one called that you can Google for called the Fisher separation, where it's a little bit more vector oriented. So there's different ways of like estimating the separation between but they're simple ratios. Make sense? So it's another thing you can do, and this might suggest, oh, I should look at, you know, I should look at the model at layer 2027. Right? It looks like there's a big separation there. Maybe they'll tell me what's going on. Okay, so what I want to share with you, so actually you can even bring this up. This is actually a nice, I prepared a thing that is kind of a model for what I hope you might do for your project, or at least resources for things that you might do. So there's this GitHub page, puns. There's also a GitHub project. You can just look at all the code. So I sort of vibe coded it, but it does have a lot of nice examples of the code in it. And so I just want to take a little interlude to step you through like how you would do this type of analysis in your projects. And some of the things we talked about last week, but because I was really disorganized by the project timings, we didn't really have that much time to talk about it. So we're going to talk about it again here. That's okay. So the steps are like this. So first we like make some data sets, and we like make contrastive data sets, and then we use it to benchmark models. And then after we benchmark models, we can use NDIF to gather internal activation data, and then we analyze it. And so I'm just going to step you through what each of these steps looks like, right? And so the example project I made up for myself, a one-person project team, is puns. So my research question is humor, right? Do LLMs know how to take a joke, right? Or at least puns, at least like really like stupid jokes, like puns, right? And so there's a whole bunch of reasons, and I wrote them in this webpage, like why puns might be actually interesting, but mostly I picked it because they're funny. And so, so my first step was, if I'm going to probe pun understanding, I need a joke book that I can use to test the models. So I can go to them and say, do you think this is funny, or whatever, right? But they have to be pretty funny jokes. So I didn't have enough. I'm not that creative. I was able to come up with 5 or 6 puns on my own. And so I did what a lot of researchers are doing now. I went to all the LLMs and I said, all right, here's some examples of a pun. Can you make me 1,000 of these? Right? And they're happy to oblige. They make thousands and thousands of puns. And I said, oh, format it as JSON, put it in a file for me. I'll merge them all up. I've got my, my ChatGPT puns, my Claude puns, my Gemini puns. They're all, like, I've got about 1,000 of them in total. But let me tell you, they're really bad. Here's like, the farmer woke up early every morning because he had to make hay. It's not very funny. Right? Some of them, like, they would be funnier, but they're like bad. Like, so here's, the door salesman was the best closer because he always knew how to close. But you said close already, so you ruined the joke, right? Like, it should say something like, the the door salesman was the best in the country because he always knew how to close, right? And then that would be that would be a joke. But like, you know, the superhuman AGI systems, they don't get it, right? Okay, but I get like 1,000 like low quality jokes like this, and then of course you have to inspect them by hand. Like maybe that's good. Maybe they were good jokes, and then I'd be done. I have my data set. It's great, right? But they were terrible. And there were too many for me to work through. So I did the same thing that we read about what Perez did. And so I'm just following the formula of the Perez paper, just like what you guys read last week, right? I said, I need to filter these. And there's too many, so you need to filter them by hand. So ChatGPT, Claude, Gemini, let's scramble these up, look at each other's jokes, right? I need you to rate these jokes. Tell me what's funny. Tell me what's not funny. Right? I'll make this easier for you. You have to do 2 steps. First, explain the joke. Explain it. And then tell me why it's funny. If you can't explain why it's funny, then give it a rating. So give all these numbers. So you do it, and it says, oh yeah, the pun relies on hey, it's a farming activity. It sounds like this, whatever, right? Like 3.3 out of 10, 3.9. Like, maybe not that funny. Right? But some of the others, like, they rated them high. And so I did this, and then like after I filtered it wasn't good enough. I had very few jokes that survived the thing, but some of the jokes were kind of close, so I also ran what I call the joke repair workshop. Right? Where I said, okay, now read the explanation of the joke, and then think about why it's not funny and see if you can make it funnier. Here's a couple of examples of repaired jokes, right? And I repaired another couple hundred jokes for me, right? And then re-rated them and so on. And so after a while, I did this, and I had to. So the honest truth is, it wasn't enough to get a few hundred funny jokes. I got maybe 100 funny jokes out of this, and then there were 100 other jokes that were almost funny, but they couldn't figure out how to repair them, and so I had to go and repair them by hand, right, as a human, and repair the jokes and did all the things. Okay, so that was sort of the process I did. So I got a couple hundred jokes out of this, right? Oh, and then now you have to watch out for me because I've got my 200 puns. Okay. So, so then the next step is we need to study these jokes in models where we can look on the inside of them. Like, we're not going to study ChatGPT because OpenAI is not going to let us look inside ChatGPT model. So I was like, let me just study, let me test all the different models and see which one. So the real challenge with any of these things is you can't study a phenomenon in an LLM that's too dumb to actually have the phenomenon, right? If the LLM can't take a joke at all, then there's no joke awareness to studying it. So the first thing you got to do is you got to find the LLMs that you can look inside. They're open LLMs, but they actually know the concept that you're interested in. And so I just took my 205 jokes and then used the fastest service I could find to just throw them at all these LLMs. What I did is I took the humorous word that was, the baker was poor because he didn't make enough, and then leave it blank. And then you have to say dough, right? And then a lot of the LLMs cannot do that, but some of them can. And so I just sent them all to all the. So this is the smallest LLM, and then the dark red is the biggest one. And you can see for this batch of jokes, the smallest LLM could only get 10% of them, and the biggest LLM could fill in the joke for 80% of them. And so there's a real difference between the small and the big ones. So these tiers. And then not only that, but it was an interesting chance for me to rate the jokes themselves. And so a lot of the jokes were so laugh out loud funny that even the dumb model would basically get it. Right? That makes sense? But then some of the jokes, when you take off the funny word, they read like straight sentences. And the AI doesn't get that there's a joke going on and just puts in a regular word. you know, the banker was demoralized because he had lost his job, right? They'll say. But if you're in a jokey mood, you might say the banker was demoralized because he lost his interest, right? Get it? Interest. Interest. Like in a bank. Okay? Get it? So, but that's what happens with all the models. They're like, I don't get it. I don't get it. Job. He would lose his job. Why would he care about losing his interest? It's like a model thing. Losing a job's more serious, right? And so that's where there were like 88 prompts that were like this. So I probed all the models, but it was also an opportunity for me to probe the data set, which was interesting, for a couple other reasons, right? Does that make sense? Okay. So then the nice thing about doing this and asking the dumb models to complete it is that I actually got these nice long lists of straight versus funny answers. So, what is this? The Taylor one is court case because he had an excellent suit. An excellent suit. But if you ask like the small models to answer this, they're like, he had an excellent lawyer, right? Right? He had an excellent defense. He had a good reputation. He had a good excuse. He had an alibi, right? It's like, he had all these other things. So they don't get the joke. So, but like the nice thing about doing this is you get all the other words that are not joke words, and you can have the big L. You can go filter them. You can have the big LM check. Yes, these are not joke words, and then there's some other words that are the joke words, and we can tell the difference, right? So this is like a nice opportunity to do this. So I added this to the data set, and then after that, I was like, okay, so there's a problem with this. So the problem with this is that I actually don't know, after doing this experiment, whether this is Llama 405B, the giant model, right? I don't know if Llama 405B actually knows about humor. All I know from this is it's read more text, and maybe it's seen this joke before. I don't know if it even knows that it's funny. Does that make sense? So what I did is I said, okay, but you know what? These ones are interesting. These ones are interesting because these are like hidden jokes that none of the models can see on the surface that they're jokes. And so I said, let's do this. Let's create sentences like this. So let's say this is like a hidden joke. The dangerous iPhone was arrested and charged with, I don't know, theft. I don't know. What would you charge a dangerous iPhone with? What would you charge a dangerous iPhone with? USB. Just battery. Good. Somebody's thinking you charge it with battery. So now, so if you were in this context, the diner went to the paint store to get thin air. The two antennas met on a roof, and the wedding had excellent reception, right? And then after you saw that, you're like, okay, I get it now. The dangerous iPhone was arrested and charged with, and you'd be like, battery. That's it, battery, right? But if you had a different sentence and you said the diner went to the paint store to get paint colors, right? The two antennas met on a roof, and the wedding had excellent hors d'oeuvres, right? And the iPhone was dangerous and was arrested and charged for, you might be like, I don't know, jaywalking, theft, violation of privacy, making too much noise, disturbing the peace. I don't know, what can an iPhone do, right? So you might not get it, right? And so what I did is I paired whenever you do experiments, it's useful to have contrasts. So I made these paired sets where you had one that, sentence like this, which everything was straight, and one sentence where the jokes come before. And then I looked at the last thing and I said, what does the model predict for the last word, the joke word or the not? And I had these nice data sets of like joke words and not joke words, right? And then here you go. So like this stupid little model doesn't know anything. It can never tell the joke, right? But then when you get to the big models, like, the 4 or 5B, when it's a straight context, sometimes it gets the idea that there's a joke anyway, even though there's no jokes being told. It'll tell the joke anyway, so it's a rate, right? Like 15% of the time or something, right? But then when it's a joke context, then it like reliably gives a joke, right? So this gap between this behavior in the joke context and the street context is like it's stronger evidence that it actually knows what funny is. So with this in hand, I was like, okay, we can proceed. We can do some more experiments. It's like promising. And so that basically brought me to the things that I'm talking about in the class today. Let's actually collect together our 100 jokes and look at some representations. And we're going to do more of this next week. But what I'd like you to do for your project for homework is to do some of this for your own data in the next couple of days. So what I did is I took this joke. The dieter went to the paint store to get thinner and 205 jokes just like it. And I said, what is a representation at the period? And then I analyzed all the representations of the period. I did the mass mean thing. And I got this little graph to say that the margin is biggest at layer 27 or something. And then I did a PCA visualization of pink funny jokes and blue serious ones. And I can kind of see that, oh yeah, there's kind of a separation between the funny things and the serious ones. And then there's some details, like you might want to figure out the mass mean vector with half of your data set, and then measure the separation with the other half so that you're not overfitting. Right, so there's like classic machine learning things you still want to pay attention to here. So you might want to do a holdout set.
Is this the difference or separation between the last token? Or
yes. So basically, what I would do is I would take two versions of the sentence and look at the representations at the period.
But couldn't that just be because like the answer is different, or how is that like?
Oh yeah, this is after the answer. So after the answer, the answer is definitely different. So when it says the diner went to the paint store to get thinner, and then the diner went to the paint store to get paint, and so yes. So what we could be looking at is there's all these funny words like thinner, and there's all these serious words like paint, and there's just a gap between just those words. So that might be the case. I guess my gut feeling is if you actually looked at the words in isolation without the joke, they seem just like other words, and it doesn't seem like anything special about them. But you might be right. There could be a confounder here. There could be other reasons you get the separation, and so we're going to have to do more to prove to ourselves that this is actually humor awareness. But the fact that the model can kind of separate them is a sign. It's a signal that maybe it knows that it's funny. Or maybe it knows it's funny. At least if it didn't know it was funny, it probably wouldn't have a separation like this. Right? That makes sense? We're still not sure. It might know something else that's correlated with funny, yes.
Would you take a look at the dumb model? And
oh, yes. See? Yes, I didn't do that, but you should. You could take a look at the dumb model and see that it doesn't separate. Things like that. Oh yeah, I have this nice demo that I'll show you. So even if you use my code, you can see what else I've coded. I'm so happy with this. Yeah, let's go with this.
oh, that's localhost.
Localhost? Oh, okay. I don't know if you'll see this. Demo link. Localhost. Yes. Oh, yeah. I want to show you this demo. It's so cool, but then I also don't want to slow down the class. Okay. How much time do I have left? Am I over? 20 minutes? Oh, I can show you the demo. Yeah. Although I do want to explain this other paper to you, but you get the idea. So let me the get mode. I put this here. You skip verification. Go to this thing. Oh, I don't know. If I share it on Zoom, so many things that you can do here. We have too much technology. There's too many options. Okay, so on Zoom. Am I on Zoom? I'm not on Zoom. Okay, forget it. I won't show you the demo. It's very cool though. So if you actually try the notebook and you get it to run, actually it might take some doing to get it run because there's currently a bug in NDiff that I'm having the team debug. But you can get a nice 3D view of this and look around and get a sense for like the scatter plot, has these points in 3 dimensions. Okay, so you can do that kind of thing. So this is just a 2D projection of it. Okay. So up to step 5 is like what I would encourage you guys to try to do for your projects this week. Let's talk about a couple other things about vector representation. So we had questions from Claire, Rice, and Ayush, and Avery related to this paper. So what was Claire's question? Yes.
I think I talked about vertex, but I talked about like, is there a relation between like the intention in the like intention embedding of sentences? Like if we take the joint embedding of a sentence, can we relate 2 sentences together in that way?
Right. So maybe I misunderstood your question, but I'll relate it to this anyway. Which I think that there is probably a geometry there. I don't know if there's been any good papers looking at the geometry of sentence embeddings. That would be an interesting research topic. But there's been a lot of papers on like geometry of word embeddings, and I'd expect sentence embeddings to have some of the same properties. How about Rice and Ayush and Avery? See Rice here. See Rice. Oh yeah, Rice. Yes.
I think I was just asking if we could, like, since from the results it seems like the vector arithmetics is like cleaner, like in that subspace where
you mean if in Sheridan's paper?
Yeah.
So I'll describe Sheridan's paper. That's great. Yeah, so that's what that was about. Okay, cool. Yeah, and the answer is I think so. I think it's cleaner. I don't know if it's more effective for patching. It's probably an open research question. You could ask Sheridan when Sheridan's back from the but it's a good question. And then Ayush, I'll talk about what all these things are in a minute. And then Ayush and Avery.
Avery.
Okay.
It's more about like the concept and token. It's.
Oh yes.
We're gonna go over
I'll go over that.
Okay.
Yeah. Okay, I'll go over that. Yes. So it's about, you want to hear about induction heads. Okay. So let me just describe this. So the history for this piece of work is there's a very famous paper by Mikhailov in 2013 called Word to Vet, where they train like a 0-layer neural network. It's like the simplest model on a lot of text, and then get vector embeddings for all sorts of words, and then makes a big deal about the fact that the words as vectors have this interesting geometry. Like if you take the vector for man and the vector for woman, it makes this vector difference between them. And then if you take the vector for king and you add that vector difference that you had to that, then you get king plus woman minus man. And you look around and you say, what word had that vector? And what do you think you find? Yeah. He's like, you get queen. That's pretty neat. And so he's like, oh yeah, he you can make all these parallelograms between man, woman, king, queen. That's not exact, right? The queen is a little bit off, but it's kind of close, right? And so it's like, sweet, right? This is a semantic vector arithmetic, and so after Mikhailov found this, every natural language professor in the world taught everybody this is what happens with vector embeddings, except for this caveat here, which is weirdly, if you look at state-of-the-art networks and embedding vectors in real networks, they don't really do this very well, right? They don't really do this. Like queen might be in like the neighborhood, but it's like really far. You might be closer to some other encoding of like Idaho or something, And so, okay, so the paper eventually gets to talking about what's going on here. But to lead up to it, I want to just describe Sheridan's work, which I think is really cool, and it goes through induction heads. So taking an interpretability class, I need to teach you what an induction head is. It's not optional. So you guys need to learn this. Okay, so what an induction head is, it's about copying. So like if you have a sentence that's repeated in a piece of text, like I hear the cardinals, I hear the, right, and you put that into your autoregressive model, the normal bigram statistics for I hear the would probably say I hear the car, I hear the explosion, I hear the music, or something like that after it. It wouldn't say I hear the card. That's something that you would hear. But in this context, that is the most likely answer. It will say I hear the cardinals. And why does it say that? It says that because it was just said. And it knows that English text or whatever, like real human text, often repeats itself. And so if it's getting ready to repeat itself again, that's like really likely. So this repeating thing is a thing that all the language models learn how to do. And it turns out that if you look inside to see how do they compute whether they're going to do a repeat or not, you find these interesting attention heads inside the model that do this. They're called induction heads. The way that induction heads work, and so here's like the attention heads that do this. There's like half a dozen induction heads in this model. You can see they sort of scatter plot blue around the architecture of the model. And the way they do this is when it gets to any word, it more or less asks, when is the last time I hear when is the last time that was uttered? And they would find that this is the last time that it was uttered, but it's not actually what they're asking. They're asking, what word came after the last time it was uttered? And so the attention heads will be like, oh, this word came right after I hear that. So basically what happens is every word is tagged with its context. And every time you have a context, it goes and searches, was any word tagged as coming right after this context before? And here in this case, it'll find it. It'll find the card was there. And then the attention head says, oh, well, in that case, we should copy it. And the attention head goes and looks at the representation of card. It picks up the fact that it's the word card and then outputs this prediction. Make sense? So that's what an induction head work is. And they're all over the place. The induction heads is why models tend to repeat themselves a lot. It's because they have these mechanisms inside them. And so, this is from the original induction head paper. I just wanted to copy something out of the original paper. So this is the original work that analyzed from their diagram. Okay. So now there's this other interesting thing that happens. Oh, I should have put in another thing, which is if you actually look in detail at induction heads, and Sheridan did, Sheridan found that there's a bunch of tokens that when you copy text that don't seem to be copied by the induction heads. And so Sheridan's like, how does the model figure out how to copy these things? And so what Sheridan found out was you had this other set of heads that work like this, that basically, they look back, and instead of attending to card, they attend to like innals, like a token ahead. And then instead of changing the prediction of the next word, they indirectly change the prediction of two ahead words. So there's these weird like two ahead induction heads that kind of like skip a token. They kind of look like one extra, one ahead, which is really bizarre. So why is it doing that? Right? That makes sense? So Sharon was going to like write a paper about the two ahead things, but then was characterizing all the other things that were in this two ahead induction heads. And let me show you some weird things that happen with two ahead induction heads. So it turns out that if you have like a natural language translation piece of text, like translating Japanese boat to Chinese boat, right? And you look at what the two ahead induction heads are doing, they are actually necessary for doing this natural language translation. If you cut the heads, then it can't do this anymore. And then moreover, if you take the same thing going on in like, Spanish to Italian or something, which is translating the word cloud, nube, right, to nuvola, right, where these attention heads are still important. If you cut them, and you cut these attention heads, and you reroute the data that's transporting these attention heads from this sentence to that sentence, right? And then you let the model run. Then instead of saying nuvola, it says vaca. Isn't that bizarre? And so this is just like the 2 token ahead induction heads. And that led Sheridan to believe that, oh, what the 2 token ahead induction heads are transporting is not the second token ahead. It's transporting some language independent notion of the concept. Strange, isn't it? Very strange, different kind of inductions. They like transport the whole concept, the whole word, as opposed to this, right? Have you ever heard of this paper? That's weird. Anyway, so we'll talk more about this sort of observation analysis stuff. Yes, like
Could it be like it's transmitting things that require 2 things you have to hold in your head, like boat plus Spanish, or card plus the house as a modifier for something?
Yeah, so I think that there's a few other experiments that we did, which where you see these induction heads implicated in like paraphrasing and other things where there's not a parent going on. But you know, you might be right. There might be some alternate hypotheses. So, but right now,
I like the concept.
Yeah, but right now Sheridan's main hypothesis is that these are like the language independent concepts. So it was pretty interesting. Okay, so let me skip through these things. Yeah, so this is like paraphrasing. There's some interesting paraphrasing cases in here. So this is a follow-up paper to this, and which is also related to your question, and sort of related to the question. So what you guys read was a follow-up paper to this work, where so Sheridan has these concept induction heads, which supposedly, according to Sheridan, carry a language independent concept. And so Sheridan's like, the Mikolov parallelogram arithmetic doesn't work all that well. But I wonder if the vector representation read by the concept induction heads obeys parallelogram arithmetic better. That makes sense? So remember how I told you what Sheridan was doing was a linear readout from the representations? So, and I said, neural networks, they do linear readout themselves. So what Sheridan did is she said, look, let's take a look at the concept induction heads. There's a few dozen of these concept induction heads that like seem to pick out the language independent concept. They all do linear readout of the representations. And if you take the sum of them, to take the sum of their linear readout, that's a matrix. It's just a vector linear readout, right? So if we use that matrix to do linear readout of the concepts, and we get this other vector out, we don't really know what that vector means, but I wonder how it does at this parallelogram arithmetic, right? And so here's basically the plots that basically if you use the concept heads and you try to do all these country capital things, then it's basically 80% accurate at doing the parallelograms. Whereas if you use the regular full representation, it was down at 40% or something like that. So this is the Mikolov plot, right? Which is like, it can only kind of do it 40%. But if you clean it up by putting it through the readout that the concept induction heads are doing, it goes up to like 80%. That makes sense? And so, but then there was a question about why is it that some of the time, if you like do it for past tense or something, there's 2 types of heads that you could do a readout for. There's also the regular token induction heads that are about copying tokens. And when you do the readout that the token induction heads are doing, you also can increase the accuracy of parallelogram arithmetic, but for different tasks. Like for changing something to past tense, then the token readout is a lot stronger at doing these parallelograms than the copy one. Why would that be? Did anybody understand why that would be? Like, why is it that when you do readouts, okay, so we're about out of time, so this is my last question for you guys. Why would it be that the internal concept induction heads would be good at country capitals and reasoning geometrically about them, whereas when it comes to the past tense, the token induction heads would be the ones that were better?
I would say a concrete place versus a concept or a grammar that is more abstract.
Yeah, one of them is really abstract in grammar. So why would the literal token copying heads be better at the abstract thing? And whereas the concrete like places in the world is better at the abstract concept head. Like why would that? It's like it seems like almost reversed maybe or not. Maybe why would it not be reversed?
Yeah, I'm trying to remember from the paper, but it had to do with like the like literal structure of the word, like going from ed to ing is something that is in a different sense much more concrete than going from like one place to another place.
That's right. So some things are concrete in the world, like what city is a place, in what country, right? And some things are concrete in text, like whether you add ed to the end of the word, right? And so the things that are concrete in text, those manipulations, they follow this nice parallelogram geometry. When you read them out using token induction heads, the things that concretely copy text, right? And then, but when you read out the same tokens using concept induction heads, the things that try to read out conceptually what's going on in a language independent way, it turns out that the parallelograms you get reflect the structure of the real world concepts in the real world. What cities, what country, and that kind of thing. And so, so to me, this was super amazing. I told Sheridan, you should like write this in a high profile journal in Nature or something like that and go win your Turing Award. I thought this was amazing. And Sheridan's like, I don't know, I'm not that proud of this work. I'll stick it in a workshop. Maybe someday I'll listen to it. So here I am teaching it to all of you. I think it's really cool that the models have these dual tracks. They can think in two different ways, and it gives you a little insight or a little flavor for what's going on. And so, so there's other questions that you guys had. I apologize to the students when I didn't get to all the questions, but for homework, remember, try to gather a contrasting data set, find a model that understands the contrast, and think if you find what you get. Thanks a lot, guys. Have a great day.